I will be doing problem 1.54 in Griffith's Introduction to Electrodynamics. And in this problem, we want to check the divergence theorem for the function v equals r squared cosine theta r hat plus r squared cosine phi theta hat minus r squared cosine theta sine phi hat. Using your volume as one octant of the sphere of radius r, which I have drawn here. And so just to remind you what the divergence theorem is, it is the volume integral of the gradient of v d tau equals the surface integral of v dot dA. So we can start by checking the left-hand side of the equation, which is the volume integral. So first, let's define d tau, and that is dr times r d theta times r sine theta d phi. Next, we look at the different variables. We see that r varies from 0 to capital R, theta varies from 0 to pi over 2, and phi varies from 0 to pi over 2. Now we take the divergence of v, and this is in polar coordinates, so we use the equation for that, which I will write here. V sub r is the r component of v, and we will also have v sub theta and v sub phi, which are the theta component and phi components of v. And here I am plugging in the components of v. Now I will solve for the partial derivatives. And we are left with 4r cosine theta. So now we can actually compute the integral. So theta, or phi, goes from 0 to pi over 2, theta goes from 0 to pi over 2, and r goes from 0 to capital R. And we found that the divergence of v was 4r cosine theta, and d tau was r squared sine theta dr d theta d phi. Now I will take the integral with respect to r. Now we'll take the integral with respect to theta. I'll be using u sub, where u equals sine theta, and du equals cosine theta d theta. And lastly, I'll take the integral with respect to phi. And we end up with pi over 4 r to the power of 4. Now we can move on to the right-hand side of the equation. As a reminder, right-hand side is the surface integral of v dot dA. To compute the surface integral of v dot dA, we want to take the surface integral over the different surfaces of the shape and add them together. So surface integral of v dot dA is equal to the integral of surface 1 v dot dA, surface 2 v dot dA, and surface 3 v dot dA, and surface 4 v dot dA. And in the picture I have the surfaces numbered. So we'll start with surface 1, which is the surface in the YZ plane. So here we see that r is varying and theta is varying. So our dA is dr times r d theta. Because it's convention for dA to be pointing out of the surface, we see that for surface 1 it is in the direction of phi hat. Now we will take v dot dA. So for this, we will get negative r cubed cosine theta sine phi dr d theta. Now if we looked at surface 1, we see that r varies from 0 to capital R, theta varies from 0 to pi over 2, and phi is equal to pi over 2. And from this we can set up our integral. Now we compute the integral. And we are left with 1 over 4 r to the power of 4 sine of phi. Now from earlier we remember that phi equals pi over 2, so when we substitute that we get negative 1 over 4 r to the power of 4 for surface 1. Now let's move on to surface 2. Now surface 2 is the part of the surface that's in the xz plane. So we can start by writing dA. We see that this varies in the r direction and the theta direction. And again, because it is convention for dA to point out of the surface, dA is pointing in the negative phi hat direction. So we get dr r d theta and negative phi hat. And again, we compute v dot dA. And as before, because dA is in the phi hat direction, we only care about the phi hat direction of v. And in this case, we see that r goes from 0 to capital R, theta goes from 0 to pi over 2, and phi equals 0. So now we can set up our integral. Okay, so here we can plug in phi equals 0 from the beginning because that is constant, and we will get r cubed cosine theta times 0 dr d theta, and we will get a 0 dr d theta, which equals 0. So we're done with surface 2. Now we can move on to surface 3. Which is the surface that lies in the xy plane. dA for surface 3. Surface 3 varies in the r direction and the phi direction, and points in the theta hat direction. Now we compute v dot dA. Again, because dA points in the theta hat direction, we only care about the theta hat direction of v to compute the dot product. Now we look at our variables. R goes from 0 to capital R. Theta stays constant at pi over 2. And phi goes from 0 to pi over 2. Set up our integral. And we compute. And we get 1 over 4 sine theta r to the power of 4. And we know that theta equals pi over 2. And we end up with 1 over 4 r to the power of 4. Now we move on to our last surface, surface 4, which is the sort of outside of the sphere. So again, we find dA. The surface is varying in the theta and phi directions, or phi and theta are varying in theta and phi are varying in the surface, and r is held constant. So we get r d theta times r sine theta d phi, and this is in the r hat direction. Again, we compute v dot dA using compute v dot dA, and we worry about the component of v in the r hat direction. And in this case, r is constant, equals capital R the entire time. Theta goes from 0 to pi over 2, and phi goes from 0 to pi over 2. We set up the integral, compute the integral. Now to compute the integral with respect to theta, again use u sub, where u equals sine theta, and du equals cosine theta d theta. We're left with pi over 4 r to the power of 4. We can substitute r equals capital R, and our final answer for the surface integral of this surface is pi over 4 r to the power of 4. So now that we've calculated our integrals for all the surfaces, we can add them together to get a total. So from the first surface, we found 1 over 4 r to the power of 4. For the second, we got 0. Third, we got 1 over 4 r to the power of 4 plus pi over 4 r to the power of 4. And adding these up, we get pi over 4 r to the power of 4, which is the exact same thing we got for the left-hand side of the equation. So therefore, this is consistent with the divergence theorem.